Hello everyone. Today we're going to be looking at Z scores and standard normal distribution. So a Z score is a number that shows where a particular point of data lives in relation to the mean. If a data value has a Z score of 1, then it is one standard deviation above the mean. If a data value has a Z score of -1, then it is one standard deviation below the mean. If a data set has a mean of 12 and a standard deviation of 3, then a data value of 18 would have a corresponding Z score of 2. Because if we add 3 to 12, that would be one standard deviation above, which would get us to 15. And if we add 3 further, we get to 18. A data value of 9 would have a corresponding Z score of -1. Because if we start with a mean of 12 and subtract 3, that would be subtracting one standard deviation, and 12 minus 3 is 9. A data value of 6 would have a corresponding Z score of -2. Because 12 minus 3 once gets us 9, and if we subtract 3 again, that gets us to 6. So we're 2 standard deviations to the left of the mean. A data value of 24 would have a corresponding Z score of 4. In order to get from 12 to 24, we would need to add 12, and 3 fits into 12 4 times. A data value of 13.5 would have a corresponding Z score of 0.5. Because we would need to add 1.5 to 12 to get to 13.5, and 1.5 is half of 3. And last, a data value of 7.5 would have a corresponding Z score of -1.5. Because if we start with the mean, which is 12, and subtract one standard deviation, we get to 9. And if we subtract another 1.5 from that, that would give us 7.5, which is 1.5 standard deviations to the left of the mean. So if a data value is below the mean of the data set, then the Z score is negative. And if a data value is above the mean, then the Z score is positive. So here's a Z score formula. If x is any data value, then x equals mu plus z sigma. So z is the Z score, x is the actual data point, mu is the mean, and sigma is the standard deviation. So you should hopefully notice that you can get from here to there by doing a little bit of algebra. If you subtract mu from both sides of this equation, you get x minus mu equals z sigma, and then if you divide both sides by sigma, you get to that formula. So in this example, the mean running time for a 10K race was 41.3 minutes for the men, with a standard deviation of 3.2 minutes. And the mean running time was 45.2 minutes for the women, with a standard deviation of 4.6 minutes. Johnny ran the race in 39.2 minutes, and Janine ran the race in 42.7 minutes. We need to determine who performed better compared to their same-sex peers in the race. So let's start by listing what we know. We know the mean for the men was 41.3, and the standard deviation for the men was 3.2. And for the women, the mean was 45.2, and the standard deviation was 4.6. So we're comparing Johnny, who got a time of 39.2 minutes, to the men. So 39.2 is x, and we're comparing Janine, who ran the race in 42.7 minutes, with the women. So the Z score for Johnny is given by x minus mu divided by sigma. So x is 39.2, minus mu is 41.3, divided by sigma, which is 3.2. So we subtract 41.3 from 39.2 and divide by 3.2, and we get a Z score of -0.65625. And the Z score for Janine, we use the same formula, but we use the women's data. That'll be 42.7 minus mu, which is 45.2, divided by sigma, which is 4.6. And that gives us a Z score of -0.54347, and some other digits. So who did better compared to their peers? Well, it's important to remember that in this situation, it's better to have a negative Z score because you want a lower time. So because Johnny has a more negative Z score compared to Janine, Johnny did better in relation to his peers. In example number 2, Johnny was told his Z-score for a recent mark on a test was 1.23, and the standard deviation was 8.5%. If the actual mark on the test was 72%, then determine the class average. So let's start by writing what we know. The Z-score is 1.23. The standard deviation, sigma, is 8.5. His actual score was 72%, so that's x. And we need to figure out the class average, which is mu. So we can use the formula z equals x minus mu divided by sigma, and we solve for mu. So let's substitute what we know. Z is 1.23, x is 72, mu we don't know, and sigma is 8.5. We can multiply both sides of this equation by 8.5. So 8.5 divided by itself is 1. And that gives us 10.455 on the left, and that's equal to 72 minus mu. Now we can subtract 72 from both sides. 72 minus itself on the right is 0. And then we get negative 61.545 is equal to negative mu. And if we divide both sides of this equation by negative 1, we get mu is 61.5%. So that's the average on the test. So now let's look at this in relation to the normal distribution. So in question number 3, Mark and Mitchell ran the same 10-kilometer race as Johnny and Janine. Mark's Z-score was negative 0.75, and Mitchell's Z-score was 0.56. So we're assuming the race times were normally distributed, and we need to determine a few things. We need to figure out the percent of male runners first with times between Mark's and Mitchell's time. So I have something for this. Ladies and gentlemen, may I introduce World War Z-score. This basically performs the same function as normal CDF does on your basic TI graphing calculator. There's a link to this in the description. As a Canadian, I can never really remember whether I should pronounce it Z or Z. I usually call up former Prime Minister Stephen Harper to find out. Fairly regularly, I might add. The last few times I've phoned, he's just answered, "It's Zed." Then I go, "Thanks, Steve." I call him Steve. We're pretty tight. Although I didn't get through before I started recording this today. I hope he's okay. I might need to switch my number again. That usually works. So in this first question, we need to determine the percent of male runners between Mark's time, which is 0.75 sigma to the left of the mean, and Mitchell's time, which is 0.56 sigma to the right of the mean. And look at this, it's already done. 48.56% of the runners sampled live in this region. So if we do that with our calculators, we go second vars and pick normal CDF, which stands for cumulative distribution function, as opposed to PDF, probability density function, not what we want. And we enter our upper and lower limits. So our lower limit is negative 0.75, and our upper limit is 0.56. We leave the mean and standard deviation as is, and enter on paste, hit enter again, and there it is. We get the same result. If we multiply that by 100, we see it's 48.56%. So let's try another one. What percentage of runners got less than Mark's time? We're going to use this again, and to start we need to adjust this boundary as far to the left as we can. Now ideally, I would adjust this to negative infinity, but from a practical standpoint, that's just not going to happen. So it's helpful that this curve gets thinner and thinner the further left we go, and the area under the curve makes smaller and smaller contributions. So it should be sufficient if I just let the lower boundary be like negative 10. So you can open up this side panel, and we're going to make A negative 10. So negative 10. Now for Mark's time, we have a Z-score of negative 0.75, and that's what we need to make our upper limit. So we're going to change B to negative 0.75. So let's see our result. It's 22.66%. Now if we were to do that with our calculators, we would go normal CDF, so second vars, down, and then enter. And we need to go as far left as we can with the lower limit. So we're going to go negative 1 exponent 99, which is a very large negative number. So we go negative 1 exponent 99, enter, and then our upper limit needs to be negative 0.75. so negative 0.75. Leave the mean and standard deviation the same, enter on paste, and then enter again, and it's 22.66%, which is what we would get if we multiplied that result by 100. So we can record our results so far. For this one it was 48.56%, and this one it was 22.66%. I'll leave it to you to show that number 3 is 28.77%, and number 4 is 77.34%, and number 5 is 71.23%. And for this you could either use the Z-Score app in Desmos, or you could use the normal CDF function in your calculator. So on to 3b, Mark was faster than what percentage of the other runners? So this is basically the opposite of 3a2. If we have Mark around here, the runners that were faster than Mark live in this region, and the runners that Mark was faster than live in this region. So if 22.66% of runners were faster than Mark, if we do 100 minus this number, that gives us the percentage of runners that Mark was faster than. And 100 minus 22.66 is 77.34. So Mark was faster than 77.34% of the other runners. And we can see this in Desmos as well. If we adjust the lower limit to negative 0.75, and we adjust the upper limit to some large number of your choosing, 1,000 ought to cover it. So we can see we get the same result, 77.34%. Now for part C, Mitchell was faster than what percentage of the other runners? So again, this is basically the opposite of 3A number 5. There were 71.23% of runners that had a time less than Mitchell's time. So if Mitchell is around here, this lower region is 71.23. And if we subtract this from 100, that gives us the region up here, which is 28.77. So Mitchell was faster than 28.77% of the other runners. Now if there were 5,000 runners in the race, then Mark was faster than how many runners? So we've already determined that Mark is faster than 77.34% of the runners. If we multiply that number as a decimal by 5,000, that'll give us the number of runners. So we go 5,000 times 0.7734, and that gives us 3,867. And knowing that Mitchell was faster than 28.77% of the runners, we multiply that number as a decimal by 5,000, so by 0.2877, and that gives us 1,439. In question number 4, we basically need to work backwards. So we need to determine the Z-score of a data value if 35% of the data is to the left of the Z-score. So we're going to try this question in Desmos first. Our lower limit basically needs to be at negative infinity, but again, because we can't do that, we'll just set the lower limit to negative 10. And we need to figure out what the upper limit is going to be in order to make this percentage go to 35. So we can play around with B a little bit. Maybe set our upper limit to something a little more reasonable. So maybe go from 0 to 5. So again, we need to make that 35%. So it looks like we need to go to the left of the mean. So let's maybe make our lower limit on B negative 2. So we'll go a little bit further left and see what we can do. Looks like we can get it close. So I would expect the Z-score to be in this neighborhood. Thankfully, there's a more reliable way to do this in our calculator. We go second vars, and we select number 3 and hit enter. So the area we are looking for is 0.35, and we leave the mean and the standard deviation the same. Enter on paste, and enter again. So we get negative 0.38532, and so on. Let's maybe see if we can reproduce that result in Desmos. So we're going to change this number to 0.38532,04726, and it looks like we did it. So let's record our result. So I guess roughly what that would have looked like is like that. and then this is 35%. So I'm going to leave question number 5 for you to do on your own. We'll do question number 6 together. So for number 6, Jack ran the same race as Johnny and was faster than 40% of the other male runners. We need to determine Jack's Z score and actual running time. So remember, in the normal distribution, if we're talking about running times, slower runners are to the right. So we need to arrange 40% like this to be to the right of Jack. So this will be a good hint for you for number 5. If we want to find the Z score, we do inverse normal. And if we're working with a percentage to the right of the Z score rather than the left, as we did in number 4, we do 1 minus the percentage as a decimal, which is 0.4 in this case. And then we leave the mean and standard deviation the same. And this gives us a result of 0.2533. So now if we want to calculate his actual running time, we know his Z score, which is 0.2533, and we know the mean from earlier was 41.3, and the standard deviation as well, which was 3.3. So now we can use the formula Z equals x minus mu over sigma. And then we can sub in what we know and solve for x. So Z is 0.2533, x is what we need to find, mu is 41.3, and sigma is 3.3. So next we can multiply both sides by 3.3, and 3.3 divided by itself is 1. On the left side we get 0.836 and some other digits equals x minus 41.3. And now we can add 41.3 to both sides of this equation, and we get x is equal to 42.14. So I'm going to leave question number 7 for you to do on your own, and here's some handy reference charts. So that's it for me for today. I'll see you next time.